Good morning and welcome to all of you. At the outset, let me take this opportunity of thanking Petrovidya for giving me this platform to share some of my thoughts on a very interesting topic, road from fractional flow to EOR. I'm sure that many of you must have heard of enhanced oil recovery, but very few of you must have seen the beauty of enhanced oil recovery in yielding incremental oil production in actual fields. Enhanced oil recovery is a very complex subject. It's a confluence of physics, chemistry, mathematics, and many engineering and geosciences. It is very complicated when talked in detail and looks rather simple when few things are said about it. While interacting with the academic world and the industry in the last decade, I felt there is a need to deliver this talk that can be easily understood, and it should create the right platform to study the EUR processes in detail. In this presentation, I will talk on what, when, why, and the need of EUR, and try to demonstrate to you how EUR is linked to the fractional flow of oil and water. What is EUR? When an oil field is discovered and put on production, it produces its own energy, the energy of the system, and that's primary recovery. In comes the artificial lift like separate pumps, gas lifts, radar pump, and other sort of lifts to aid the vertical lift and thereby enable it to produce fluids to the surface. Then walks in the secondary recovery for water injection or gas injection, for pressure maintenance or for flooding the reservoir and to reduce the oil saturation. Then there's a third back of recovery processes called tertiary recovery processes, which are mostly EUR recovery processes, thermal, gas injection, and chemical. But these days, even in the past, some of the processes has come out of the bag from the tertiary recovery bag and have been employed right in the primary stage or in the secondary stage, like steam and polymers. They are widely being used in the primary or in the late primary or in the beginning of the secondary recovery processes. So you are no longer targets in mobile oil. It also targets mobile oil as well. When to think of EUR? The time is now. Sir Winston Churchill once said, the best time to plant a tree is 20 years ago. The second best time is now. In the E&P industry, the best time to plan and begin implementation of EUR processes is during the initial development planning when a field is discovered. And if you have not thought of it at that stage, the second best time is now. Why now? Design and implementation of an EUR project takes time. Right from conceiving an idea to transfer it to the desktop, translating into a one-dimensional laboratory viability project, then to a three-dimensional field pilot project, implementation, evaluation, and then drawing up plans for field-wide expansion. It's engineering design, construction, erection, commissioning takes time, 5 to 10 years. So you can see it takes time to make the efforts and the investments, to reduce the uncertainty and the risk, right from developing the idea in our mind to yield the commercial oil in the field. So that's the message. Think of EUR right at the beginning and start planning for the right EUR project, or maybe more than one EUR project. It depends on the resources available to the thinker. Some of the important terms that it will be linked to this fractional flow talk, or the recovery, and related to recovery, the initial oil saturation, remaining oil saturation, residual oil saturation, the relative permeabilities to oil and water, mobility contrast, and the fractional flow. So here recovery has been defined as the change in saturation of oil with respect to the initial oil saturation. SOR, I don't term it as a residual oil saturation because recovery with every time step, the oil saturation is changing and it is the remaining oil saturation at that instant. It is yet to reach the residual oil saturation at the end of water flood. And that we term it as SORW, as the residual oil saturation to water when the capillary number reaches to 10 to the power minus 7, beyond which water is not able to reduce the oil saturation further in the pores when we need to do something different. So how we are concerned with these terms, we will see there. Mobility is the most important term for a reservoir engineer, is the mobility of the water and the mobility of the oil. Oil, you know, there are different type of oils, from extra heavy oil, medium gravity, light, volatile oil, and mobility are different for these different type of oils. And so water is more or less almost constant, negligibly varying with pressure and temperature. But with oil, the oil properties are totally different in different type of oils, and mobilities are the major concern. So mobility is defined as ratio of relative permeability to that phase to the viscosity of that phase. And what is the mobility contrast, which controls the displacement in the pores, or the ratio of mobility of displacing phase to the mobility of the resident phase. So that's mobility of water to the mobility of oil. Now this can be equal to 1, less than 1, or greater than 1. When it is equal to or less than 1, it is favorable displacement, a piston-like displacement, where nature cannot give a better situation than that. But as the mobility contrast goes on increasing beyond 1, you know, the displacement goes on becoming unstable. And as a result, fingers of water starts developing, which breaks through into the producers, leaving behind significant amount of bypassed oil saturation and early water breakthrough into the producers, so enabling the operators to produce more of water and less of oil with time, and resulting in lower recoveries. Now, what is fractional flow of water? Fractional flow of water is the mobility of water to the mobility of the liquid. So lambda water by lambda water plus lambda oil. Now in the subsequent slides, we will see more of this mobility contrast. This picture depicts the mobility ratio, favorable and unfavorable, stable and unstable. When it is close to 1 or less than 1, the displacement of oil by water is very stable. You can see from the curve, with 1 pore volume of water invading the pores, recovery efficiency is very high. And you can see from that curve. Whereas as the mobility ratio, mobility contrast goes on increasing more than 1, then the displacement becomes very unstable. And the fingers you can see in the top right hand corners of water encroaching through the reservoirs and breaking through into the producers for early water production. So you can see more pore volumes of water injected, invading the pores, more time requirement for to achieve the same recovery. But can we wait for such time? Can we afford to produce so much of water? It costs. So your processes walks in at this stage, you know, to somehow make the entire process stable. Relative permeability, a very important term which we will be encountering in the fractional flow, is the dimensionless number. You can see from the y-axis the relative permeability to oil and water, and the endpoints. The SWI is the blue, increasing saturation of water, and on the reverse is the decreasing oil, increasing oil saturation. So in fact, at the endpoint KRO, we have initial water saturation of 20% and oil saturation is 80%. This is two phase occupying the pores. And whereas the other endpoint where we have SW, water saturation 80%, SOR, that's the SOR of around 20%. So these are the endpoints. You can see the intersection of the two KRW and KRO beyond 50%, which close to, which indicates that it's a water weight system. And you can note the endpoints, beyond, between these two numbers, SWI and SOR. This is the water which goes into the water saturation that goes into the computation of normalized water saturation. So this is a linear displacement of oil by water, water in, water out in the pores, leaving behind the residual oil within the pores, which are held by the interfacial forces as well as the capillary forces, and how much of water flowing out of how much of the liquid coming out, that's all the basic fractional flow. So what we are going to see in the subsequent computation of fractional flow is for a linear homogeneous system with no dip, no gravity effects, sandstone reservoirs, very well sorted sands, tortuosity 1, high permeability, and no compartmentalization. So I think this should be the launching pad for you to start developing on a radial system and subsequently on a multi-layered system of fractional flow. So now, before we move on to the actual fractional flow, this is the need for UR. You can see the fractional flow curve, water cut with recovery. Well, x-axis can be represented by water saturation as well, but for easier to understand, I have represented with recovery for you to appreciate better. And we can see at 90% water cut, we have around 6 to 7% recovery for that particular type of oil which is being considered. So the important parameters which goes into the fractional flow computations are the oil viscosity, water viscosity, initial oil saturation, initial water saturation, residual oil saturation to water, as well as the relative permeability to oil and relative permeability to water. So now we will see how we go and compute the fractional flow. Here it is. Now let's see that case where oil viscosity is 1 centipoise. Now let me tell you at this instant, there are different type of oils with different type of composition, with different type of colors and different type of viscosity. For a reservoir engineer, it is extremely important to appreciate the term viscosity. Many times I have come across in the industry that oil is being represented by API. Well, API is a marketing term. It's truly correlates with viscosity. Sometimes it may not, but it doesn't give the direct information as to the resistance to the flow of that particular type of oil. So therefore, it's always important for the petroleum engineer and reservoir engineer to appreciate the oil viscosity of the system. So here is a case with oil viscosity 1 centipoise, which is a measure of the resistance to flow, very simple, very mobile, with slightly more than that of water, which is 0.4. And for that particular reservoir, initial oil saturation is 80%. So initial water saturation must be 20%. And the residual oil saturation to water is 30%. Now, how we do it with changing recovery, NP by N, we compute the different water saturation changes in the reservoir. So from the initial 20%, it goes on increasing with recovery because only two phases are flowing in the pores, oil and water. There is no gas, all above bubble point. Pressure is above bubble point. And then we compute the normalized water saturation, which is the ratio of difference of oil saturation, this current saturation with the initial water saturation to the 1 minus initial water saturation and the SOR number. So that is that normalized water saturation. And there are several correlations to compute the relative permeabilities. Like relative permeability to water is a function of SW star. So there can be quarry, they can be stone, they can be parcel, they can be Delshad and Pope. There are so many correlations, but I suggest that you take the correlation which which fits in into the production performance of that particular reservoir. So KRW here is a function of normalized water saturation to the power 3, and 1 minus SW star to the power 3 is KRO. And then FW is computed, as I showed you in previous slide, is the ratio of lambda W by lambda liquid. So from there we get the fractional flow of water for this particular system of 1 centipoise. Now you can see the curve here. Now, as per Wellgate, if I draw a tangent from the initial water saturation 20%, which you can make somehow here. This is the recovery, but you can change it. From there to this inflection point, you will get the water saturation at the leading edge of the front. So from there, you can compute that number. And if I extend that number to 100% water, that will be the somehow behind the flood front. So the flood front will have a minimum water saturation of this number. So but one thing you can see here, with this mobility contrast to 1 and 0.4, which is very close to 1 actually, that is around 2, 2.5. So 2.5 mobility, the displacement is quite stable and favorable. You can see till 10%, there is no water production in the reservoir. And beyond that, slowly the water production starts increasing, and finally breakthrough takes place, and it's all water. So when it is 90% water, we have already achieved a recovery close to around 37 to 40%. It's a good number. It's a big number. But what next? Obviously, the question comes, what next? Would you be satisfied with 35 to 40% at 90% water cut and say, I've done my job? No. Obviously, responsibility is to increase it. Target maybe 50%, target 60%, maybe target 100%. But reservoir engineer has to have a solution here, has to provide a solution here how to do that. So only way now, we cannot alter the mobility contrast. It's already close to 1. So thing which we can change here is SOR number. I can bring down the residual oil saturation to around 10% maybe, is say, and see the curve shifting. That means how to bring down the residual oil saturation. It can be if reservoir temperature is within allowable limits, salinity within allowable limits, and no divergent ion presence, you can well do it through alkali surfactant polymers. Surfactants are responsible in reducing the interfacial forces and dislodge the oil which is held by the capillary forces within the pores, and they make it somehow a bank and make it reach the producing end. So this is one way of doing solution to what next. Another way can be reservoir temperature is extremely high, or maybe surfactants are not conducive to such reservoirs. So after the end of a good water flood like here, well, you can, if it's a light oil like this, 1 centipoise or less, well, miscible carbon dioxide. Well, I'm seeing some projects very close coming up in India that in the tertiary stage, carbon dioxide miscible project will be undertaken work. Obviously, to increase recovery percent from 40% to 50% plus, and additionally getting some more benefits of carbon sequestration as well as whatnot. So you can see how to rejuvenate a matured field now when the oils are very light, when the oils are very volatile and light. So let's go back to now the original condition of 0.3, and water viscosity I'm not changing because it's almost, let's keep it constant almost. Now we can increase it to around 50 centipoise oil. Now we are entering from light to medium gravity oil. Now you can see the fractional flow curve shifting to the left. That means early water breakthrough. Now the displacement is getting unstable. The mobility contrast is around more than 100. So water is tending to move 100 times faster than the oil for the same drawdown. Now if you see at 90% water cut, recovery stands close to 20%. So from 40% for a 1 centi poise oil, it has come down to 20% for the same water cut level. Now, obviously, you are saying, obviously, this is because of the adverse mobility contrast. What to do about? How to increase it now? How to control the water production in the field? Well, this is not a good picture of 20% recovery and 90% water cut. So the first attempt, what some people want to attempt is increase it to, viscosity to 25 centipoise by adding polymers. Okay, so by adding polymers, you see the curve has shifted to the right. So here, what is happening? The mobility contrast has gone down now. It's close to 2. So at this instant, the mobility fractional flow curve has shifted to the right. That means water cut is depressed in the reservoir. That's yielding to higher recovery. Now you are getting at around 90%, around 37% recovery. Okay, so you can see now the benefits. How fractional flow is linked to this mobility contrast. Now, what next? After polymer, no one gets satisfied at the end of the day by achieving 37% and 90. So, well, some operator can think of doing ASP and bring it down further, the residual oil saturation, and shifting the fractional flow curve subsequently to the right, adding some more recovery, around 5 to 10% more recovery over polymer. So you see the fun, how your processes are linked to fractional flow. So this is one school of thought. Maybe another school of thought will be, let's go back to the original 0.30 and water viscosity is 0.4. So we go back. So origin condition, one of the biggest operators in India has attempted, is very successful in conducting air injection in this type of reservoirs, and what they are attempting to reduce the numerator of the mobility ratio, mobility contrast to around 2 centipoise by attempting air injection and decreasing SOR at the same instant in the swept zone. So at the same instant, air is doing two things. Whereas the chemical was polymer first modifying the flow by regulating the mobility contrast, and surfactant coming later to reduce the residual oil saturation. Here in air injection is targeting both the viscosity of the oil as well as reducing the SOR number. So you can see the benefit, how you can change the fractional flow, how it can shift that fractional flow curve to the right. Let's go back to the original situation. Okay, so here we are in the original CM 50. Now you can see as the oil is going from lighter to medium, you can see in the light oil only there was an option at the end of the water flood by changing the capillary, increasing the capillary number by surfactants and miscible CO2. Now we are entering into the medium gravity, wherein polymer first is attempting to modify the water flood by changing the viscosity of water and making the displacement very stable, and then surfactant reducing the SOR, whereas otherwise air injection can reduce the viscosity of the oil, the numerator, to modify the mobility contrast and reduce SOR at the same instant. Now, if we go into around, let's say, to around in the heavy oil regime of 500 centipoise, the viscosity, the fractional flow curve shifts to the left. That means at 90% breakthrough, we get a very low recovery of around 7 to 10%. This is not a rosy picture at all. So what happens? From day one, that's what I said, that some of the UR processes has come out of the tertiary UR bank. It has come right at the primary stage. So some operators like me, don't be biased like me, but sometimes I I have been in some other place and straight away implemented steam injection to make it to reduce the viscosity of oil and get significant amount of incremental oil through steam injection and shifting the fractional flow curve to the right. And that's substantial from 7 to around 35% at 90% water cut. Well, there can be another school of thought, and that's very prevalent these days. You know, let's go back to 500 centipoise. Uh, well, no, what I did in steam, two things were happening. Sorry, I forgot to tell you. These 2 centipoise as well as reducing the SOR number. So steam was targeting two things, not only reducing the numerator to modify the mobility contrast, reduce the mobility contrast, as well as targeting the SOR number. But some operators these days and many companies, it's becoming very famous these days, very popular these days, you know, to start polymer injection right from day one. You know, it all depends on the availability of resources like capital, human knowledge, the appetite to take risk, and many other factors which goes into this decision making. But I have seen even some operators have attempted both parallelly to see the efficacy of both the processes. So someone straight away, if the reservoir temperature is very favorable, very low, that means cold reservoirs as well as salinity is very low, like fresh water, well, polymers like in some countries in South America has done, and they're getting very successful results. Like here, straight away from day one or day two, right at the end of primary, attempting polymer flood and getting substantial amount of oil. Polymer is relatively easy to operate than steam, but both have its merits and demerits. Both have its advantages and disadvantages. But both yields incremental revenues. So this is what 5,000, and let's go back to now the original condition of water and 500. Now if it is extra heavy oil or extremely viscous oil, well, you have a very quick water breakthrough at around 90%, less than 5% recovery. What to do? Why to wait for a water flood? Well, go and do inject steam or polymer. See, many reservoirs all over the world are very popular with steam injection of this type of reservoirs, wherein viscosity goes down to very low number and reduce the SOR to 15%, even low, 10% or so. But for demonstration purpose, I'm showing just 15%. And you can see how significant amount of oil in US, Canada, Venezuela, China, Russia, extremely popular with steam flooding, and this type of oil has is the most successful EUR project has been steam in such reservoirs. But things are changing. Technology is changing. Technology is development of technology is leading to reducing the cost of polymers and surfactants. So chemical EUR is gaining popularity these days, even in this type of reservoirs. So let's go back to the original condition. And in 5,000 in Canada, this type of reservoirs are being operated by injecting polymers and getting substantial amount of oil. So again, it depends which one to go for. It depends on you. It depends on the expertise of that company, the ease of operating, the risk to take, the appetite to take the risk, how much resources it can be made available. You know, it all depends on that. It's not a hard and fast, but a same operator can do both the things together at the same time. So you get a fair idea now, you know, as to now what this fractional flow can do. This gives a fair idea as to the wide extent from a light volatile oil to an extremely heavy oil. The mobility contrast is the most important term that a reservoir engineer has to understand right at the word go. That should be in the mind, and that should give in the mind the fractional flow curve immediately. And to have that fractional flow curve, you obviously know what sort of EUR will obviously walk through into such reservoirs. So this is what it is. Now I'd like to show you in a nutshell, what this ER processes actually does, responsible. So there we are. In fact, this is what I want to show you. You know, the water flood is the baseline. Everything that needs to be compared with water flood. The engineered water flood, we call it as the smart water flood or the low sal water flood, which are very specific in nature. Sometimes in very high salinity reservoirs, they are one of the good options, but the recovery, incremental recovery is low. Immiscible gas flood, well, if you have resources available to you, you are just like carbon dioxide easily natural deposits, well, you can go for that. Like in some countries in Europe, which significant CO2 natural resources deposits, they have gone for immiscible gas CO2 gas flood. But the recovery factor is moderate. Hydrocarbon, myself has seen in immiscible, they are inefficient ones, very low incremental, maybe plus minus 1 to 2%, not beyond that. 6 CO2 also, no moderate, more than that, but not like miscible one. Miscibles are extremely the most efficient and high yielding EUR processes, whether it's hydrocarbon WAG, or carbon dioxide WAG. They are extremely efficient EUR processes. And once the reservoir pressure, the miscibility pressure is above the reservoir pressure, well, certainly miscible gas flood is the key to your additional oil. Thermal, yes, for viscous oil so far, so long in the world, thermal has been the mainstay, whether it is the shallow or the deep, steam and air. Air has seen now from moving from heavy oil to light oil, air injection, and many operators are testing it in medium gravity too, where polymers are not effective because the temperatures are either very high or maybe too deep or reservoir pressure has declined. Steam, yes, very shallow, less than 1000 meters is extremely high recovery factor because it targets not only the viscosity, it also reduces the SOR, as well as I've seen it changes the wettability. In very dirty reservoirs, clay reservoirs, from oil wet, it has changed to water wet because of high temperatures. So you see the effectiveness of thermal. Chemicals, yes, it's coming up very fast, very quick. What it was 30 years back, today it's totally different. The cost has gone down significantly, and polymer not only modifies the flood front, not only makes unfavorable displacement to favorable displacement by increasing the denominator of the mobility contrast, it also even can reduce residual oil saturation. These are some particular type of polymers, but most commonly it is used as a precursor to alkali surfactant polymer fluids to modify the existing water flood, cut down on those fingers, make the flood front more or less stable, piston-like, and get some easy oil to be produced. So this is what I wanted to show you, how EUR is linked to the fractional flow and how, in nutshell, what these EUR processes are responsible in affecting. Thank you so much, and questions please.